So I'd really like to introduce our panelists. So we're really lucky to have Rich Ritchie from Rowden Technologies. He's head of machine learning, and hopefully he's going to give us lots of insight on the practical applications of reinforcement learning. We have a very good, reliable Dr. Brian is here. And of course, he's our director of training at Krisolis. He also works in UCD, so I'll let him tell you all about that. And as I said, I'm CEO of Krisolis. So without any further ado, let's get going. And I'm going to stop sharing my screen and start talking with Brian and Rich. So we might start with you, Brian. So if you just want to introduce yourself first of all.
Thanks, Aoife. So like you said, I'm the Director of Training at Krisolis, so design a lot of our training courses and deliver lots of our training courses. And I also lecture in computer science at UCD in the School of Computer Science there, and head up our Science Foundation Ireland Centre for Research Training in Machine Learning, where we have lots of PhD students working across all aspects of machine learning. And reinforcement learning is one of the interesting areas that we do some work on.
And Rich, I might just ask you to introduce yourself as well.
Sure, yeah, I'm Rich. I'm head of machine learning here at Rowden. We're in Bristol, in England, and we're doing a lot of projects in reinforcement learning, sort of walking that line really between research and trying to find real-world applications of where we might use reinforcement learning algorithms, primarily for sort of defense contracts and things like that.
Fantastic, thanks. So, Brian, we might start with you. And first of all, of course, for those of us who don't know too much about reinforcement learning, what is it?
Yeah, so reinforcement learning is really interesting. So it's a kind of a branch of machine learning. So people often talk about machine learning in terms of supervised learning, unsupervised learning, and reinforcement learning. And then people invent all kinds of little categories in between those as well. But I suppose what distinguishes reinforcement learning most from, let's say, supervised learning is rather than, or typically at least, rather than using a labeled data set that we'd used in supervised learning. Instead, we take a model, which we usually kind of wrap up in what we call an agent, and deploy that into some environment. And by that agent and our reinforcement or our machine learning model that's encapsulated in it, interacting in that environment and receiving feedback on those interactions, it learns to perform some tasks. So the sort of classic, maybe early reinforcement learning applications, and an easy one to think about might be in robotics, where we might have a robot and we'd like that robot to learn to do something, rather than collecting up a big data set that would tell that robot, you know, in this situation, do this thing, in this situation, do this thing. We'd basically deploy the robot into the environment, let it at first sort of wander around randomly, aimlessly, but through doing that, receive feedback, which in reinforcement learning we typically call reward, from the environment, and from that reward learn how to behave appropriately. And it's pretty fascinating, it's a pretty interesting thing that from very simple rewards, basically, so every time the agent takes an action, it receives a reward, which might be negative if this was a bad thing to do, or positive if it was a good thing to do. We can actually learn quite sort of long-term sophisticated behaviors with agents in that, and reinforcement learning has been applied to things like robotics. Early on, lots of the most famous applications have been things like game playing. So people probably heard of the AlphaGo system that got a lot of attention, but all kinds of other things. So anywhere where we can frame the problem as, all right, we're going to package up what it is that we want to do into an agent, and then deploy that agent into either a real or simulated environment, and allow it to learn as it goes. That's sort of I guess a whistle-stop tour that the differences typically between reinforcement learning and things like supervised learning.
Fantastic. And I suppose, Rich, given you work in a company who specializes in reinforcement learning, do you have any good examples of how you've used it, I suppose, practically with real-world applications?
Sure. So I think at the moment what we're seeing is people are taking sort of environments, as Brian says, you know, we have this environment that the agent's interacting with. So that environment could be a game or a simulation of some kind. And a lot of people we're seeing in industry now have got these simulators already that they've, you know, humans are interacting with. So things like flight simulators, for example, or maybe, you know, they can model certain situations that they train humans with in order to do the right thing. And they're interested in seeing how AI agents would actually tackle those problems as well, because one, it might just save us time time. If there's a particular solution we want, a human hasn't got to go and do that for them. But B, they might come up with really innovative solutions that, we wouldn't have thought of as humans, and we can sort of see how those solutions might help us. One of the challenges we find, the real practical challenges, often those simulators, those environments, they weren't really designed for artificial agents to play. So they run with very heavy graphics, and they're quite slow because the human can play slowly, whereas this AI, they typically want to play very fast. So a lot of our work is trying to prepare people's sort of expectations and their environments to fit. One of the examples we've been doing is having a room, a building, and we've got multiple agents who are trying to secure that building. So there might be civilians in the building who need help, or perhaps they need, certain rooms need to be secured. And we're trying to find if there's sort of strategies that the agents might come up with that could that we as humans wouldn't necessarily think if we were in the same situation.
That's brilliant. I think just to come in there, I think that brings up, I think, one of the really interesting things about reinforcement learning is that potential for the agents to come up with sort of novel solutions.
Yes.
And we could probably talk about later on. Sometimes that's a bad thing.
Yes.
But a lot of times that's the kind of really exciting thing. And people might have seen that if you watched, let's say, the AlphaGo example. One of the sort of things coming back from that was that the agent learned to play that game in a sort of a different and interesting way compared to the way that people play it.
Absolutely, yeah.
And I guess that also brings us past, say, supervised learning, where, if you give the data set and the data set has labels, the machine learning model is going to learn to do that thing, whatever you've taught it. Whereas there's an opportunity, at least.
Exactly, yeah.
Reinforcement learning.
And I think that reinforcement learning, the fact that there isn't necessarily one right thing to do at any one time step, I think that's the really defining factor. And it's also the sequence of actions that you take as well, that, what could look like a bad action actually could become a good action depending on what you do next, which I think is what we saw with AlphaGo, with very bizarre moves, sort of however many moves in, and then at the end it suddenly made sense why it did that.
Yeah, and Brian, I suppose from a research point of view, is there anything that you're seeing at the moment in a research perspective where reinforcement learning has kind of really worked?
Yeah, so I guess the one that I do some work in that is interesting is, people might have heard of active learning, which is a semi-supervised approach to machine learning. And actually just recently I've been reading a few papers where people are taking a reinforcement learning approach to that. And I think that's pretty interesting, where a bit like, I guess, some of the other techniques we have, sometimes stepping back and thinking about the problem and just being able to frame it in a slightly different way opens up the potential to apply a new set of techniques. So in active learning, the idea is we have a human in the loop involved in training a machine learning model. And the big thing we have to figure out is how do we, what are the questions we're going to ask that human through that training process? And there's a lot of kind of standard approaches to that have been around for a long time, but there's a new batch of reinforcement learning based approaches to that, which is, it starts to get very meta, because we're using a machine learning model to figure out how to train a machine learning model with a person involved in there as well. But it's kind of nice, where again you've got that idea of a thing is going to happen, so a decision is going to be made or an action is going to be taken. So in that case, picking what example am I going to put in front of a person, and then there's some feedback. So whether that turned out to be a good example or a bad example, and that happens again and again and again, which is kind of a perfect reinforcement learning scenario. I think another big area that Rich mentioned there, the idea of simulators, there's this big idea of sim to real, which in reinforcement learning is fascinating. So if you take driverless cars, for example, an approach, I don't think it's the approach that's largely taken, but an approach to training a driverless car is to use reinforcement learning. Now, the tricky bit, like I said, is at the start, you're going to send that agent out to act randomly. You don't want to send the driverless car out to drive randomly. That's not going to work. So what you'd like to do is maybe have it, train the agent in the simulator until it's pretty good. And then we know even the best simulators won't capture, all the nuances of the real world. So then transfer it across to the real world. And there's some really interesting work going on about how you do that, which is pretty fascinating.
Yeah, it's like that classic credit scoring example where you're trying to convince a set of senior executives, sure, why don't you just give everybody who comes through the door a loan for like a month, and then we'll have the perfect data set to be able to model off. But yeah, I still haven't managed to convince them to do that. So brilliant. So I think at this stage it might be useful, Brian, if you brought us through, I suppose, your tech example, just to show us how exactly reinforcement learning, kind of how we can do it from a technical point of view. So for all of you non-technicals, it's perfectly fine to go and get a cup of tea at the moment. But those of you who like your code, this is probably the section for you.
It involves a spaceship, so it's exciting either way. So hopefully, Aoife, you might tell me if you can see that code, just to be sure.
Yep.
I see that window. That's great. So what I'm going to show here is just a very simple reinforcement learning example with some Python code in behind it. Again, I guess just to reinforce what we said there, this is a picture. Aoife mentioned our book that has a new edition out and a chapter on reinforcement learning. So some of the pictures here are taken from that. And here's this classic reinforcement learning loop. So here's our agent. This is going to be our machine learning bit. It takes actions in the world or environment, gives it back some reward based on those actions. And then based on what the agent sees in the world, it figures out the next action to take. We go round and round there all the time. And by looking at these rewards, our agent should be able to learn how to do the job better and better. Now, the example I'm going to use is from the OpenAI gym. So OpenAI, people have probably come across a really interesting company doing interesting things in machine learning and AI. One of the things they've built are this set of environments for playing with reinforcement learning. Essentially, there's all kinds of different things like games or training sort of agents to walk and stuff like that. It's really nice. And it's kind of those environments are there, and then you get a hook into it, and a pretty easy hook into it. So you can put anything on your side. I'm going to use that. The other thing I'm going to use is a thing called Keras. So people might be familiar with Keras, the deep learning library. There's a reinforcement learning version of that called Keras, or not quite a version, an add-on called Keras, which implements some nice, simple, I guess, some reasonably sophisticated, but some nice reinforcement learning algorithms. The one in particular here we're going to use is just DeepQN or DeepQ networks. So a kind of a standard deep learning approach to reinforcement learning. It'd be interesting maybe when we come back after this to hear Rich's opinion on different technologies and packages that are useful for reinforcement learning, because it's maybe a much more open landscape than it is for, let's say, standard supervised learning. So here's what the environment is. It's the Lunar Lander game that people might be familiar with. It was an old sort of Atari game, I think. I remember playing this as a kid, where you have a little spaceship and the job is to land that spaceship between the flags. There are 4 things we can do. And in reinforcement learning, a thing that we're always going to think about is what are the actions that we can take. There are 4 actions available to this agent at any time. It can push a thruster left, push a thruster right, push a thruster down to go up. I spent a long time trying to figure out what the right label for that arrow was, but the thruster can go down, or you can do nothing. And if you do nothing, the spaceship falls. Basically. So you've got these little thrusters that you can push out. So you can imagine playing this yourself, and you've got your 3 arrow keys, up, down, left, and right, or sorry, up, left, and right, or just don't press any button and see what happens. And what you want to do is land nicely between these 2 flags, so not crash. So from a reinforcement learning point of view, the things we need to think about to set up the environment are, what are the actions I can take? In this case, there's those 4 actions. What's the environment, which is this game that we're going to play in, and then a state representation for the game. So the state representation is basically what the agent here is going to know about the world. Now, in this simple example, I'm using a vector representation that tells us the position of the spaceship, the velocities, there's a couple of different velocities, its angular position to the flags. But you can do this as well just using the image as input or a stack of a few frames. I've simplified it just because it's a nice bit quicker and we can actually run a little bit of it. So that's our setup. The modeling part of this is looks like this. This is a kind of a simple illustration of our model, where what the model here is going to do is, given a state, so given the current position of the world, so where's the spaceship, how fast is it traveling, where is it in relation to the flags, it's going to tell us how good or what the value of taking each one of the available actions would be. Right, there's a couple of different ways to frame this. This is a pretty standard way to do it. So given a state, right, here's what's going on at the moment. What's the value that we might apply to going left at the moment? What's the value of going right? What's the value of going up? Or what's the value of doing nothing? And a typical reinforcement learning agent policy for choosing one of those actions will be to choose the one with the highest value. Right, so that might be a sensible thing to do. Whichever one looks like it's going to be the best thing for me to do at the time. So this is what the model is going to do. And then the learning job is, through experience in the world, for the agent to figure out what are appropriate values to give to these actions in different states. right? That's the mystery. That's the thing that we don't know at the beginning. And that's what the agent is going to try and figure out. And as Rich said there in the discussion before, one of the things that's fascinating is just from these simple rewards that we get from the environment, we can learn quite sophisticated behavior, because there's lots of actions that we're going to take, let's say at the beginning of this game, that it's not going to be obvious that they're going to help by the time we land between the flags, but are going to be really important. And our reinforcement learning agents should be able to learn some of those. So that's our setup of the model I want to build. I'm going to set up a simple Keras model here. So people familiar with Keras might be familiar with this. So this is just a really simple feed-forward neural network. I have 1, 2, 3 dense layers, an output layer with my 4 actions. So it looks like this. And my input state is going to be the state vector that's coming in here, telling me about what's going on in the world. So I'm going to build that model. Again, I use Keras for this. In this simple demo, there's lots of other ways we could do it. I then set up my reinforcement learning piece, which in this case is a DeepQ network agent, right? So this is the piece that comes from Keras RL. I'm going to use what's called an epsilon greedy policy. The epsilon greedy policy means that while the agent is trying to learn about the world, sometimes it's going to do random things, and sometimes it's going to use what it's learned so far. So what we always think about in reinforcement learning is balancing exploration and exploitation. So sometimes I want to learn what I've done so far, but sometimes I want to explore new things. And we need to strike a balance between that, because if early on you keep doing what you've learned so far, well, maybe you don't really learn the good behaviors. Whereas late on, if you're being too random, you'll never quite figure out a good thing to do. So epsilon greedy, essentially randomly determined by a parameter epsilon, which I think is 10%. So 10% of the time just chooses a random action, the rest of the time chooses its best action. And then my DeepQ network is the setup that we have for reinforcement learning. So all things going well, this should show us another window. I'll just move this up here. So here, this proves that it's real, because my technology has broken a little bit. Occasionally you can see my spaceship coming in and out there. Let me think for a second. If I stop my share, just going to move this onto the same screen and do that again. So hopefully you can see this now. Aoife, you might smile and nod if you can. So here's my spaceship at the beginning of the learning process, where it's just doing random things, and you can see it's pretty terrible. Essentially, it just falls out of the sky, occasionally twists around. So now I'm going to try and learn. So I'm going to use my DeepQ network agent to try and learn this game. The last key steps, we talked about actions, we talked about states. The last key step is a reward. So how do I structure the rewards here? This is a bit of text taken from the lunar lander code that describes the reward setup in this environment. So essentially what happens here is that I get a reward of -100 if I crash. I get a reward of +100 if I land properly. I get 10 points if my leg gently hits the ground. I get 200 points if I land properly between the flags. And every time I fire the engines, I lose 0.03 points. So the kind of loop here is that there's the state. I take an action, either left, right, up, or nothing, and I get a little bit of a reward. Lots of the time that reward will just be -0.3 because I'm just firing engines, right? I haven't landed, I haven't touched the ground yet. Occasionally at the end, I'll either get a big negative reward because I crash, or I'll get a big positive reward because I either land or land between the flags. Now, reward design is one of the sort of arts of reinforcement learning, and we might see some impact from that in a second. Now I'm going to train it. I'm just going to do a few steps here. Actually, let me stop that and do a few less steps. No, we'll do that. It should work. We'll do a few steps. We'll do a few iterations of training. So now I've set visualize false here so we don't get to see it. But now basically my agent is playing the game. Right? So it's going to play lots of episodes of this game. It's going to try and land the spaceship. Using DeepQ learning, this is kind of an illustration of what's happening. So essentially there's the neural network, just like we talked about above. It's taking in states, it's choosing actions, and we're finding out rewards based on those. What it actually does in this case is it stores up a data set based on those and trains a network based on that. Then there's this kind of clever trick of swapping between two different networks to stop the learning from oscillating around the place too much. This is going to run. Reinforcement learning can take a little bit of time, so we're almost there. I can stop this and it'll probably do what I want it to do. So let me stop it there. And I'll jump down here and just look at it again. So you can see here, right? So after not too many iterations, right? So kind of tens of iterations here, my agent is now doing okay. Actually, it's doing better than I thought it would do in this case. So it's starting not so much. Right, so it's taken off there. At some point it might come back. It runs out of time at some stage if it just flies off into space. It's done okay in terms of learning how to do it after not too many iterations. And the big sort of really interesting thing here is this agent knows nothing about this game, nothing about, you know, how this world works. All it knows is I get a state representation telling me what's going on, and I have these 4 actions I can take. And just by existing in the world, it starts to learn to take good actions. Now, this is good because it's showing progress, but it's not nearly there yet. Let's give it one more go. No, it looked like it was going to do well and then said, no, I'm out of here. So let me stop this one. And here's my Blue Peter bit of here's one I made earlier. So I let this train yesterday for a pile of time, right? So I let it train for, I think it's a couple of thousand episodes of this game. And all things going well, if I run this, we should see my window. Yeah, here it comes. So this is the one, pretty sure this is the right one. This isn't still the other one rolling along in the background. Down it comes very gently, and we'll see it again. Down it comes. There's a couple of interesting behaviors that we might see here. Down it comes. Kind of wobbles around a little bit. Some of the interesting behaviors come from the reward. So you can see it's in no hurry, right? So it's very gently coming down. And one of the reasons for that is you don't run out of fuel in this version of the game. And the negative reward you get for using fuel is very small, right? So that minus 0.03. If I wanted to encourage this agent to land faster, I could play with that reward. The other slightly strange thing, which going back to the point we made earlier, is you'll sometimes see here it kind of brushes the ground and moves side to side a little bit. So you can see here, right? So it's landed, but it's not happy to stop yet. And the reason for that is it gets a reward every time the leg touches the ground. So we start to learn this slightly strange behavior where it says, well, I could land, but actually if I wobble from side to side here, I get a few extra points. So I'm going to do that. And you'll see it does that a lot. So it's almost there, but it sort of moves side to side before it stops. Let me stop that. And just if there's a picture here. This one. No, that's when I stopped. We'll stop there, but you can just about see here, if I look at these two, this is the last thing I'll show, just the effect of that reward. Here are those first 12 episodes we ran where the episode is playing the game. And you can see the rewards the agent got when it was behaving randomly were minus 4, 3, 200. Sometimes it was a bit lucky, did a bit better. Whereas now you can see if I look in this other window, here's my trained agent getting nice positive rewards. Right? And that's all that's driving the learning. And I think that's a really interesting thing to remember is that all the time, all the agent knows is these are the actions I take. It receives those reward signals and it learns reasonably sophisticated behavior, which I guess is the big promise of reinforcement learning. That's a real simple example. You can do loads more, all kinds of different reinforcement learning algorithms, more sophisticated environments, more sophisticated states. You can do all kinds of interesting things, but hopefully that gives people a sense of what's involved.
Super. Thanks, Brian. Always has to go back to a computer game, doesn't it? So I suppose just one question, I think Brian touched on it there, Rich, around the different, I suppose, technologies or packages that you're using in this space. Is there anything that you find useful, I suppose, particularly in a more commercial environment?
Yeah, absolutely. So we use a framework called RLlib. which is an open source framework. So that's Reinforcement Learning Library, I guess it's short for. And I think it's come out of Berkeley University in California. And it seems a lot of the sort of more serious papers who are targeting kind of industrial applications seem to be implementing their algorithms in RLlib. RLlib's based on a framework called Ray. Ray is a highly parallelizable framework. So you can basically take your Python script and you can run it on many, many threads across potentially many, many machines in a cloud environment across a cluster. And it does that for you in a very straightforward manner. So as soon as we start trying to run these algorithms on, problems that we can't just run it on our laptop, we want to put it on the cloud and we have to run the environment itself, might even have to be run on quite a powerful machine, then it's nice if there's a framework that takes care of that for you. And that's what RLlib will do pretty easily. Actually, it's very well documented. You just essentially have a JSON file. You can tell it how many CPUs, GPUs, how many machines you want to run across, and it will sort of take care of that. And there's some very, very powerful algorithms in there that a lot of people seem to be updating and maintaining very well. And so we try and write our algorithms. What I would say with RLlib is I wouldn't necessarily start there as a way to learn, because it runs on multiple threads and it's all distributed and everything else. Things like debugging and just sort of being able to step through the code can be quite complex. However, if you've got an environment and somebody's asked you to sort of see the potential of maybe running an RLlib algorithm against it, there's a huge array of things you can try, and it will you can just add a bit more compute power to it and it will step up quite quickly. Whereas if you're using sort of some of the, it was a learning curve for me because I went from sort of trying to do things like computer games and sort of nice smaller environments that I created, and then suddenly you're faced with this thing that you have to run it on. Just if you wanted to play the game yourself, you'd have to run it on quite a powerful computer to get the AI to play it, and it might want to play it in parallel. So typically with these algorithms, we'll actually have the AI play, say, 10 versions of the game at once, just so we can stream as much experience as possible in a shorter amount of time. So RLlib is very good at scaling horizontally, as we say, that sort of horizontal scaling. But that's a good start. But I wouldn't, like I say, start there if you're trying to learn. And I would start very much with something like what Brian's just shown.
Excellent. And I suppose it probably leads nicely into what are the main challenges that you've come across from an implementation point of view? So
reinforcement learning, I'd say, is I wouldn't get disheartened if it doesn't work first time. I'd be surprised if it works first time. I've heard people say before that supervised learning kind of wants to learn and reinforcement learning doesn't want to learn. So very often you can be very close to a working solution, but you've just maybe got a couple of parameters that you need to tweak. And it's amazing just what a difference that can make. The reward function, I think, as Brian mentioned, is really key. And one of the jokes of reinforcement learning is actually you're just trying to create a reward function that works, because I think, as we saw in the lunar landing example, it was already exploiting the fact that it could kind of land many times effectively if it sort of did that sort of sliding across at the end. And we'll find that a lot. All it cares about is getting the highest score possible. It has no concept of sort of the spirit of the game or what the rules of the game are as such. It just wants to maximize on that reward. So you will find yourself changing the reward function a lot. And the challenge is not to change it, what we call reward shaping. If you've got a particular solution in mind, you could create that reward such that you're sort of leading the agent along. You're sort of putting a series of rewards in its wake, sort of leading it down a particular solution. But if you do that, you're not necessarily going to find the innovative solutions that you really want. So it's a balance between how do we create a reward that's general enough that it's going to sort of come up with some interesting solutions, but not so general that it can never actually learn anything.
Fantastic. And I suppose just at that point, I am going to open questions up for the general public. So anybody who's online, feel free to use the Q&A session to ask some questions. I suppose one of the things that I always like to ask at this point is to think about, is there any favorite application that you've read about or that you've even implemented yourself? And I suppose, Brian, I'll start with you for this. Is there anything that you've read it and gone, that's really cool? I suppose an application that you either didn't think about or that just kind of caught your attention. So in terms of reinforcement learning.
Yeah, so I think there's loads of really nice ones about the driving cars and playing games and things like that. The ones that I find particularly interesting are when people have sort of framed an unexpected problem as a reinforcement learning problem. And they're the ones where I find you have to stop and go, how on earth how did you figure that out in terms of state and reward and things like that? And one of those is, again, the AutoML. So a lot of the auto machine learning solutions, so those kind of big black boxes that you say, I want to build a supervised machine learning model, I'm going to press a big button and go and do all the hyperparameter tuning and maybe even feature engineering and things like architecture search and things like that. There's a lot of the interesting approaches that are framed as reinforcement learning problems. And I remember the first one I came across, it was a nice paper, but I had to read it 4 or 5 times just trying to get, how on earth have you made this a reinforcement learning thing? It doesn't strike me as one of those. And I really like those kind of examples. That AutoML piece is a real nice example of that.
Yeah, I mean, I'd agree on that. Just to say, the AutoML with the Google, so Google's AutoML service that you can use on their site is doing exactly that. So it's actually creating a neural network architecture to do supervised learning, but the way it's designing that architecture is through reinforcement learning. So it's a very nice combination. From my point of view, I saw a great paper. There's a paper called Imagined Worlds, which I think it's a Google paper, and they've combined GANs. So I'm guessing you guys probably cover GANs at some point, generative adversarial networks, so generative models. So we see them with deep fakes a lot. So being able to produce very realistic pictures of people or whatever it's trained on. And the way they combine it with reinforcement learning is that they basically got the agent to sort of start to imagine how the simulator might behave in different circumstances. So it sort of was able to train itself on its own experience with the simulator and then use that GAN to generate possible future things that it hasn't seen yet, which I thought was really interesting. So it was able to make a very robust model. So with the spacecraft example, this would be, it could imagine different landscapes that it had to land on, and it could learn for itself, which I think is a big problem we have, is this idea that the simulator is so slow. It'd be great if we could get experience from somewhere else, and if it's able to imagine for itself, that could be potentially a quicker way for it to learn without having to interact with the simulator, which is what humans do. We have a bit of experience, and then we sort of imagine and build models in our brains, and we learn through our own sort of imagination.
Fantastic. I actually have a question here from Fiona. So thanks, Fiona. So Fiona's coming from a fintech background where customer behavior is slowly changing. Is there any use cases for using reinforcement learning over traditional supervised learning?
So the ones I'm aware of, at least, and I'm not sure if these probably match the slow customer behavior, are like the trading platforms or anything to do with auctions or markets, where there's automated systems in those. There's loads of people building reinforcement learning agents to do that, but they're typically, I guess, slightly more fast moving things where you're buying, you're selling, you're taking these actions, and there's an opportunity to deploy using historical data, an agent into the world to simulate that, or then to deploy them out into the real world. I'm not sure in terms of slow moving customer behavior, maybe you mean things like credit scoring and stuff like that. I'm not aware of a lot of reinforcement learning applications there, but maybe Rich, you are.
I mean, I agree. I've, in my spare time, occasionally looked at these algorithmic trading books, thinking I might get rich one day. And one of the interesting things is that you've got to realize the agent is only ever aware of the current state that you give it. So if you were doing, very naively, if you were doing, say, the stock exchange, it would just see all the current prices, maybe for the last couple of hours or something. And you have to ask, is that enough information? If you had that and you had no, understanding of what's in the news today or the world events that have currently happened, would you be able to make the correct decision? So one of the fundamental, if you're doing pure RL, you'd hope that all the information it needs is in the state. It's this idea of like a Markov process. Is it truly everything it needs to know? So a game like chess, everything in front of you is all that you need to know in terms of making your move. But maybe in sort of finances or any kind of predictive model where it's looking at historic sort of data, that data obviously only covers so much of the current situation. So you have to be careful. But I think there's definitely very interesting potential there. The other one, of course, is things like targeted advertising. Probably is one of the most successful examples of RL, choosing which advert to show to who based on maybe some information about their browsing history or something like that. The reward is obvious. Did they click on it? Did they not click on it? Or how long did they look at it? How long did it hold their gaze for? So you can imagine that actually, I don't know if that falls into fintech necessarily, but it's kind of, that's a very nice example of how we might use reinforcement learning.
And I think that targeted advertising, maybe more broadly, recommender systems. I've seen more and more recommender systems work using reinforcement learning, particularly those sort of maybe big platforms like, I'm not sure if Spotify use it, but things like Spotify where there's loads of people giving loads of feedback about recommendations that they have. There's a lot of people doing interesting RL work there.
Yeah, I find with Netflix, you can start to shape it almost. You can see they're sort of picking up on what you click on and what you don't click on. And yeah, very interesting.
Yeah.
Yeah, you shouldn't say you can have fun doing things like that, but it can be interesting.
Yes.
Put in a few searches and see, let's see what they'll show me. I suppose one thing that I suppose people always come to us a little bit about is sometimes if you were starting, so like that, I suppose Fiona's question is kind of similar. Like you're working in an area, you're probably using other ML techniques. How would you get going with reinforcement learning? So Rich, I might start with you for that.
My advice would, I think it depends on the type, how you learn really, I guess. If you're the sort of person who likes to really sort of take your time and read a very long book, perhaps, then, there are books you can do. But otherwise, I would say go on, do an online course or a course with people like yourself. Go through an example where somebody has made a sort of very clear path of how to get to success. So if you start maybe with your own environment and your own ideas, unfortunately, it might be that you never quite succeed, but you kind of want to see what it's like to actually get something working. That lunar example, would be a great place to start, or there's plenty of ways you can learn that stuff, but I would just try and get an end-to-end solution working, and that tends to be just follow someone else's guide who's done it before you, and then you can kind of reverse engineer that and try and make that work for your use case, or at least understand the maths a bit better through that example.
Excellent. And Brian, I don't know if you have any.
Yeah, no, I think I agree with all that, and I think taking on sort of one of the let's say something where reinforcement learning fits a bit easily. So there's a nice OpenAI gym, has like loads of games and things. So there's a nice Super Mario Brothers one if people like that, or there's a couple of nice car simulators. Or there's the Amazon one where there's a car simulator and you can actually buy the little robot car. And I think it's $200 or $300. So it's probably, you'd probably want to be quite into it. For those and use those to understand reinforcement learning, because I think a couple of things that Rich mentioned there about, like, there's a lot of dials to twist. So you can play with your model, or you can go mess around with the reward, or you can go and look at the training, and maybe a little more flexibility than we have in other things. So you can kind of disappear into it, and choosing or sort of learning on one of those things where it's not hard work to frame the problem as a reinforcement learning one, I think is much better before you try and say, right, well, now I'm going to try and do my thing. The other thing is I really like that, like, there is a nice bit of magic of watching the thing do the thing. So like that, watching the spaceship try to land, and then you go back and you mess around with your code and it does it a bit better, or whatever the environment was. Those kind of environments are really nice to learn, because it really does suck you in and trying to get better. It tends to be an easier thing to learn, I find, for a lot of people.
Yeah, says the person who probably lost a lot of time as a youth in computer games. Not
That's true.
Or anything. But unless there's any more questions, so no more have come through. I think that was a great session, and we may actually finish up on time. Go us, which is always nice. So I'll just keep an eye out just in case there's a couple of questions. But just to finish up, it's always nice to be able to finish up. One thing I did mention was our book, and also from a reinforcement learning. And I'm just going to share our slide deck here for a second. So the second edition of the book that myself and Brian is actually due out. You can pre-order it on Amazon at the moment. It's not a sales line, but it kind of is. But actually we've added a chapter. So Brian actually added a chapter to this edition on reinforcement learning. We've also added some bits and pieces on deep learning and on supervised learning. So there's lots of new stuff in there. For those of you who love the first book, this is like even better. Those of you who didn't get the first book, just get this one. So yeah, so that's out now. You can get it on Amazon. Also, just in terms of feedback, we will send you a feedback survey. If you could fill it in, that would be fantastic. We really, really appreciate it. And thank you. So I really want to thank Rich for giving up his time today, because I know reinforcement learning, it's a really new area. I know people are starting to get to grips with it a little bit, but particularly those commercial examples of using it, you know, it's really, really useful to have those. So hopefully people, and hopefully, you know, people online now can have a real sense of how they can get going with it. And as ever, thanks, Brian. It's always good to have a bit of check there in the middle. So appreciate it. So on that note, I'm going to say thanks everybody for joining in. Hope you enjoyed it. Hope you found it useful. Any questions, you know where to find us. You can